Hello, everybody. Welcome to a knowledge transfer seminar today with a very special guest that we have for you. This talk is part of a series of knowledge transfer seminars that we have been conducting since 2016 in the knowledge transfer group. I'm Lynn Kretschmer. I also work in the knowledge transfer group, and we thought we would give you a nice idea of how it is to work with industry when CERN works with industry. Knowledge transfer at CERN could not happen without technical experts like many of you here, the combination with their technologies and industry. And the goal of this talk is, or generally this series of talks, is to encourage a bit and to inspire a bit of an entrepreneurial culture and a knowledge transfer culture at CERN. And we are very, very pleased to also announce after this session, there will be another session on the 12th of June on flash radiotherapy. Just for your information, there's multiple series once in a while where we talk about how we can work together with industry and the diversity of applications that CERN technology has outside of CERN. For the housekeeping, we have the possibility we are recording the session on Zoom. For all the people that are online, I hope you can hear me well. Helen, you might have asked already. Okay, they can hear us. Perfect. Hello, also online. Very happy to have you here. Please mute yourself during the discussion and the presentation. And then afterwards, you can ask questions by either raising your hands, also here in the room, of course, or by writing in the chat. Yes, exactly. Now about today's seminar. Today is going to be about precision instrumentation and the integration of CERN's single frequency Raman laser. The talk will be about FabNS, which is a Brazilian deep tech startup specialized in optical characterization of materials. And they connected to CERN and CERN technology through the CERN Venture Connect program, which is a startup support program that we have here at CERN. And the company leverages a single frequency Raman laser, which was developed in the SY department, specifically by the Sources, Targets, and Interactions group under the supervision of Eduardo Granados, who is also here today. Thanks a lot for joining. And who will be speaking today, please welcome with me Vitor Monken, who is the lead mechanical engineer in FabNS, and he will tell you a bit more about what they do and how they use the CERN technology at their company. Please give a warm welcome to him.
Hello, everyone. Can you hear me okay through the mic? Okay, perfect. As Lynn kind of introduced me, I am Vitor Monken. I am the lead mechanical engineer and head of engineering at FabNS. And today I'll be talking to you about precision instrumentation and the integration of CERN's single frequency Raman laser into our technology portfolio. This talk will be divided in 3 topics. First, I'm going to talk to you about FabNS. Who are we and what do we do and why? Also, a little bit of introduction about tip-enhanced Raman spectroscopy. What is it and what can it do? Later on, I'm going to move on to the compatibility argument on why we are licensing the single frequency Raman laser and what we expect from it. And then I'm going to finalize with the horizon about where can we go with this collaboration from now. First, a little bit of introduction. FabNS is a deep tech startup based in Brazil, and we develop Raman technology, Raman spectroscopy-based technologies. We have a core interest in tip-enhanced Raman spectroscopy systems. And today we are a team of 20 people strong. Right here is a celebratory picture that was taken with the whole team during the event of our first exportation of a portal system to Germany. So this crate here actually contains a nanoscope. And right now it is installed in Humboldt University in Berlin. FabNS is located in the city of Belo Horizonte, which is right in the southeast portion of Brazil here in the state of Minas Gerais. It's a landlocked state, but it's extremely beautiful with nice hills. We are an academic spin-off from the Federal University of Minas Gerais that can be seen here in this nice image of our campus, where we can see a lot of the tech buildings and the main office. And we are currently located at BH Tech, which is the technological park of the city of Belo Horizonte. So our house is currently on the 2nd floor of this nice building here. Well, going straight into the matter of the talk, I'm going to first talk a little bit about Raman spectroscopy. This can be obvious to some people here, but I'm just going to go right through it. So basically what Raman spectroscopy is an optical technique that is used to probe the vibrational properties of materials. Basically, what do? We shine a laser into a sample Here I have a nice graphene, pristine graphene sheet drawn out. And what happens when the laser interacts with the sample is it can either just bounce away with the same amount of energy in the form that we call Rayleigh scattering. There's not a lot of chemical information there. However, the photons that collide with the material can either gain a little bit of energy or lose a little bit of energy. And the packages of energy that it gains or loses contains valuable information about the vibrational modes of this material. So for example, we have these two vibrational modes, one that is related to the G band of graphene, which is this lateral stretching mode, and the 2D band of graphene, which is related to this breathing mode of the hexagonal lattice. And each one of these modes of vibration, they have different energy values associated with it. And when a photon interacts with these modes, it can either gain or lose different packages of energy. So what happens is when we take the light outputted from the system, which is the combination of all these scattering phenomena, and shine it into a spectrometer and divide the light, we have a signature of the material that we call the Raman spectrum. And here, not by chance, this is a pristine graphene sample. And we have a peak related to the G band, which is the presence of this vibrational mode within the lattice, and a peak related to the 2D band, which is, of course, naturally related to the presence of this vibrational mode in this crystalline lattice. Raman spectroscopy can be used not only to study 2D materials, but also to study molecules and oxides and things of that nature. It's a very powerful, non-destructive optical technique that we use extensively in characterization of nanomaterials. Going a little bit further, I introduce tip-enhanced Raman spectroscopy, just to go back to micro-Raman, as we call it, the conventional Raman spectroscopy technique. So basically, we have here in this diagram to the left, that I'm not, okay, there we go. We have two point scatterers, individual scatterers that are very close to each other, and each of them is scattering away light. However, they are too close for light to be able to resolve between them. So what happens when we analyze the output of these two particles together is we have sort of a blurred out signature of this material in spatial wise. And what we get when we scan a laser through a sample on this configuration is sort of a blurred image, as can be seen there on the left. However, when we approach a metallic tip to one of these scatterers, we greatly enhance the local Raman scattering phenomena. So what happens is basically the light emitted from this scatterer shines brighter than its neighbors, and then we are able to resolve it spatially using light, which is very neat. And then what happens is the system becomes diffraction unlimited, and then we get nanometric resolution, and this blurred image on the left becomes this image here on the right. And then you can see that this image that we were measuring is actually a pristine graphene sheet that was bombarded with a helium gun to induce localized defects and draw out a map of the world. This measurement was quite beautiful, in my opinion, and it ended up being the cover of Carbon in one of the editions, where we published a review article about defect engineering in carbon-based materials. So basically, tip-enhanced Raman spectroscopy, enhance signal, and increase spatial resolution. But giving a little bit more of detail so you can get a grasp of the scale of this. Here we have a diagram, a simple diagram. In gray here, we have a graphene sheet with a monolayer graphene sheet. And in blue here, we have a regular glass substrate, like a cover slip. And naturally, there's a very well-defined graphene edge here. And in orange, we have the hotspot generated by focalizing a laser into the sample. Roughly, this hotspot is diffraction limited, so it cannot go underneath 500 nanometers or so, depending on the wavelength that we are shining. And 500 nanometers account for approximately 2,000 lattice constants of graphene. So basically, if we take a line across our laser beam, we have 2,000 unitary cells of graphene. And then what happens is when we use this laser to scan this sample and we look at the D band, which is the defect band, which correlates to a vibration mode that only appears on the graphene edge, we get a blurred out image. Why? Because this mode only appears on the very edge, and the edge is just a fraction of the area imaged by this laser. So what happens is we approach our tip, and then here on the very center of this hotspot, you can see a very tiny red dot. and we magnified this, and then we can see what the TERS hotspot is. So this is the actual area illuminated, and from where we're collecting data using tip-enhanced Raman spectroscopy. This image here is in scale, so you can understand that this is the crystalline structure of graphene. So it's a very nanometric result technique. And then when we scan this TERS hotspot, which is scanning the tip over the sample, we can generate images when we look at the D band, such as this, where we can clearly see the signature of this defect region on the very edge of graphene. So this is basically two arguments here: spatial resolution, but not only spatial resolution, we also greatly enhance the local signal, as we can see here on this plot on the left. In black here, we have the far field signal, and in red, we have the near field signal, and they are in scale. And what happens is we can see here the D band, the region related to the presence of defects on a crystalline network. And when we go to the far field, it's buried within the noise. Or even so, it's not, it may not even be there. It's information that can be lost with the evanescent waves. So there it is, enough about tip-enhanced Raman spectroscopy. I hope it was understood, at least a little bit. So now, just to give you a glance of what we do at FabNS, this is our flagship product, the Portos Gnome Nanoscope. It's a platform built around tip-enhanced Raman spectroscopy, but it's actually the marriage between a Raman spectroscopy system and an atomic force microscopy system. Here's a very nice CAD rendering of the current configuration of the system. And here is an image of the system that is installed in Humboldt University. It's currently doing some measurements, and one of the application cases I'm going to show was actually measured there. So the Portos system is based on 4 pillars. The first is obviously optical instrumentation. It's basically 70% of what we do. However, there's also a very important ingredient on this recipe, which is our plasmonic resonant nano antennas. It's a weird name. I'm going to explain a little bit further on. Also, we have precision control electronics that we have to manufacture, design in-house to control our equipment, to actuate high voltage piezos and things of that nature. And finally, we have an analysis software that we developed to be able to gather information and understand what we are trying to study from the plethora of data that's generated by this instrument. Currently, it has a very open optics architecture. That's the idea, because we want the researcher to be able to freely assemble their experiments and try different things, different optical detectors, different techniques. And basically what we have here is a laser combining unit that we hope to replace with the single frequency Raman laser. That's our best bet. And we have 2 beam lines here. The first one is the excitation conditioning line, where you can modulate laser power, you can modulate polarization, account for polarization shifts. And then the laser then shines into our microscope, things happen, Raman spectroscopy happens here, and then it goes to the output excitation detection line, which is completely free. This is where the playground begins. The scientist can do whatever it wants during its research, whatever modules that are relevant can be introduced here. But normally we do have some standard modules, which is a spatial filter to enhance signal clarity. And of course, chromatic filtering to be able to select which part of the spectrum we are analyzing. And then the system just brings this signal into an optical detecting unit. Normally we use spectrometers, long-range spectrometers coupled to high-end CCD cameras, but this can be any kind of optical detector that's relevant to the research. Okay, so now the most interesting part in my opinion, which is the plasma tunable tip pyramid. What happens is, I mentioned that TERS is the marriage between a Raman spectrometer and an atomic force microscope. However, just putting those things together does not make it a TERS system. We need something to communicate between those techniques. And in our case, this is the plasma tunable tip pyramids. Short is PTTPs. That's the brand name for it. So basically, this is an atomic force microscopy probe that has a very special geometry. So what we have here is a micrometric pyramid that has a plateau, and then we have a nanopyramid on top of it. So this nanopyramid here is what resonates with the laser, and then generates high enhancement. This system is geometrically tunable. It's very easy to handle, as can be seen here in this image. They come in these little chips, so you can just handle it with your hands. And it has a scalability that allows us to generate several of these structures with ease. This technology was patented in 3 offices: Brazil, United States, and China. Unfortunately, not Europe yet. We're working on that. And the basic functionality of this system is that the PTTPs work as plasmonic cavities. What does that mean? So basically, we have this parameter here called L, which is the nanopyramid's length. And this is then tuned to resonate with a laser line. We have here a simulation of a hotspot of the concentration of the electrical field on the very apex of this system. And basically, what we have here on this graph is that this system can be tuned on the first mode and second mode to different laser lines. So basically what this does is we engineer this probe to resonate with a specific laser line that's being used. We put it on the system and then it resonates. And then we can get some very nice images and some very nice results. However, upon further studies, we discovered that the PTTP is not only a monoplasmonic cavity, it's also a bicavity. What happens is we have naturally the nanopyramid here with this parameter L, but we also have the plateau on which it sits with this new parameter we call W. So what happens here is, of course, we have the resonating nanoantenna, but we have also this structure that acts as a cavity. So what happens is this area here, it not only becomes a mechanic fixation system or a reservoir of electrons, it actually functions as a pump of electrons when the system is co-tuned and they behave as a hybridized cavity. And what we have is something close to this that we can see here in this optimization plot, where we sweep the nanopyramid length and the plateau length, and we get this locus of maxima. So this gives us avenues to further optimize the system and to achieve different wavelengths that can be resonant with our probes. So basically what we have, a single probe is resonant to one specific laser length. However, we can make several different probes that can be resonant to different applications. This can be resonant to the laser line that's exciting the system, but it could also be resonant to a Raman shift associated with a specific mode of vibration. So you would actually enhance a single line on the Raman spectrum. These are wafer-based produced. So what happened is we use a photolithography of a mask on a wafer to generate the pattern. And then we do wet etching of the system to generate these cavities that have the geometry of the desired PTTP. We flash gold on it, deposit a layer of gold, and then we template strip, which in basic terms is we add glue and remove the strip. So with this, we are able to produce a batch that has hundreds, or it could even be scaled up to thousands of PTTPs in one go. And we could reuse these templates. So we just clean, flash gold again, and then it's ready to use. And not only that, it's not only scalable, but also it's very repeatable. So when we analyze the dispersion of the diameter of the probe in one batch, we can see that 75% approximately have a diameter of around 10 to 20 nanometers, which for TERS is quite high. And now we can move on to the application cases. I selected 4 application cases that I find very interesting. So we try to tell a story about the system, the technique, and what can it do. First, I'm going to talk a little bit about graphene nanoflake, which is a very hot topic in the industry because it's one of the avenues of most immediate application of graphene in the industry. Then we move on to confined carbine, which is the research that's being conducted in Humboldt University in Berlin. And then an exotic application that I like a lot, which is cicada wing nanostructure. So it's a natural occurring nanostructure that we understand it a little bit more with nanospectroscopy. Then we go to this other measurement that's coherence length in graphene. And finally, twisted Moire patterns in twisted biliary graphene. So first, graphene nanoflakes, I'm going to give you a brief explanation of what this is. So basically, what we have here on the left is a schematic that displays this property here called LD, which is the average distance between point defects in a graphene lattice, and this other parameter here, which is called LA, which is the average size of grains within this crystalline structure. With these 2 parameters, we can understand very well through years of study that have been conducted by several researchers, the defect properties of the produced graphene. So basically, if we have LD and LA, we can understand clearly what material we're dealing with. And after several calculations and theoretical simulations, we were able to create these plots here, we call the whale plots, and they're abacus. So basically, we correlate properties called LD and LA to Raman spectroscopy obtainable parameters. So basically, what we do is With this abacus confirmed, we take a Raman spectrum of the determined material and we can locate it within this abacus. So it's a very fast way to diagnose the defect level of produced graphene with only one single spectrum. However, we get one single spectrum. Imagine that we have a nanostructure that's 30 nanometers long, and we shine a laser that's 500 nanometers. What happens is not only we can measure several different nanoflakes, but also we only get an average signal of one nanoflake. We do not understand the distribution of defects within this structure. So we went on and performed TERS measurements with a nanoflake. So here, there's an image that was taken. This is a window of 150 by 150 nanometers, where we imaged 2 graphene nanoflakes, and we are able to actually discern where within the structure we have defects and how they are distributed. So when we put this into our whale plot, what would appear as a single dot becomes broader. Not only with this, we were able to confirm the validity of this abacus, but also we were able to understand that nano-Raman gives us a much more information about the level of functionalization that can be engineered into this nanostructure. So this can operate as a feedback for people designing different processes. And of course, when we talk about a level of engineering that we can do, that we could understand the islands of functionalization within the structure, we were able to apply this more efficiently in the industry. There are several applications for graphene nanoflakes. More obvious one that's currently being used is they use it to dope paints to make them corrosion resistant. This can sound silly, but when we think about oil rigs and ships, they need to be repainted constantly to prevent damage to the structural material. With a more efficient paint, you paint less often. Now let's move on to confined carbide. This is a very hot topic currently. It's being studied, as I mentioned, in Humboldt University by Professor Sebastian Higgs' group. Well, basically what we have in carbide is they are single chains of graphene, carbon atoms. They are not naturally occurrent, so they have to be synthesized, and they are synthesized confined in a nanotube. So basically, what these researchers did with TERS is they were able to characterize a single carbide chain here and understand its Raman spectrum, understand a little bit of the nanometric distribution within it, but most importantly, they were able to validate and determine that what they were studying was a single carbide chain. And with this, they can prove the validity of their experimental data. Unfortunately, there's much nicer data than this, but I cannot show because it's not published yet. So soon enough, we will be able to see them on a publication. So this is interesting because carbide are the single most powerful Raman scatterers in nature, and they are promised to be used in the development of 1D transistors. That it's a way that we could break the Moore's law and miniaturize electronics, but we're still a far way to go. Now we have the exotic application, which is a graphene curved cicada wing. So basically, one of the students, what he did, he went to the parking lot and he found a cicada wing, and then he took it to the lab, cut it, put graphene on top, and then studied. This is interesting. It's not just silly. He was not crazy by doing it. This is interesting because cicada wings, they have natural occurring nanostructures. Here we have an atomic force microscopy image of this heterostructure that was built. Here we have the spikes that are natural to the cicada wing. And here we have the graphene sheet laying on top. On this 3D view, we can see it clearly. And what is interesting about this is that cicada wing nanopillars are a natural occurring plasmonic surface. So we're able to understand a little bit more how these structures communicate and interact with the material that's laying on top. We use TERS to assess this, to understand better how they couple, the signals couple. And there are some measurements here that could verify the presence of hotspots or dark spots, depending on what you're looking at. And this is very interesting because it's a biomimetic approach to CERS. So basically, CERS is all around. We just have to grab a wing and put it on a microscope. Next, measurements in graphene devices. This is a very interesting, a very delicate, non-direct measurement that can be conducted with TERS. Basically, what we do is we do an experiment called tip approach. What we do is we lay the tip, enhance the signal, collect the signal, and then we step up and measure again, step up, again and again. And then we create these curves here that we call the tip approach curves. And it's interesting because if you see clearly, and if you see in detail, you can understand that the ratio of decay of the enhancement factor between different bands is different. And analyzing the difference of this ratio of decay, one can infer the coherence length of the material in that specific situation. And furthermore, what can be done is we can apply gate voltage to this material to induce to generate a more density of charge carriers, and this modulates the coherence length. So this is an interesting finding. Well, it proved theory, but also it's a step forward towards the development of 2D devices. Because once again, Moore's law, we want to miniaturize electronics, but silicon is a challenge. We cannot miniaturize silicon as much as we would like. So there are several avenues using 2D materials that are of good promise to break Moore's law, and this is a very hot one of them. And finally, I move on to twisted biliary Moiré patterns. This is sort of the jewel of the crown as of now, because what we did is we measured a sample of twisted biliary graphene with an AFM, and you basically see nothing. However, when you go into nano-optics, you can clearly see the strange soliton lines here within this material. But we don't only see them, we can understand what's going on in the electronic level. And this was a very interesting paper where the researchers were able to understand the superconducting states that can be induced in graphene, or isolation states that can be induced by modulating the twist angle. And this ended up being the cover of Nature in this edition, where we were probing twistronics. And this is a personal favorite. And with this, I finish my application cases. I hope you understand a little bit more about the power of how powerful tip-enhanced Raman spectroscopy is and how it can be applied. And now we move on to the technology itself. Why am I here? What am I doing here in CERN? Well, I'm here training with this guy. So basically, we are licensing the single frequency Raman laser, which is a technology. I don't want to explain to you your technology, but it is a monolithic diamond Fabry hub resonator-based technology. So basically, we have a very fancy diamond. We shine light into it, and we get more light. It's amazing. It has very good properties, such as a very narrow line width, which is interesting for Raman spectroscopy. It has passive frequency stability. And also, there's another interesting feature of it that's wavelength tunable. We can select the pump wavelength, so then we get different lines, but we can control the temperature of this diamond, and we can shift this emission wavelength ever so slightly, and that can be used for several interesting applications. Now it's a good time to give a shout out to Dr. Eduardo Granados and the SY department and the whole SCI group that was responsible for the technology that we're licensing now. And of course to Lynn Crashmark, thank you very much for your efforts in this collaboration. And let's move on to what we expect to get from this technology. What are the integration impacts? First of all, we intend to get performance gains in terms of measurement. We want to be able to measure different samples, especially using a technique that can be called fluorescence-free Raman. I'll explain in a little bit. We also want to extend our reach, tapping into different markets, enhancing applications, where we can use the system to perform cars-based techniques that can be applied to the medical field. And finally, we have the commercial pitch here, which is pretty straightforward. It's a cheaper laser. We can use it in our system, cheaper system. It's a very strong commercial argument. The requirement envelope for lasers to be applied in Raman spectroscopy is quite demanding. First, we need spectral properties. We need a very narrow line width. We need for the emission light to be extremely pure in terms of its emission spectrum. And we need this wavelength emission to be stable. Otherwise, we'll just have the laser moving around and our measurements will be contaminated. We have also very demanding requirements in terms of beam quality, because we want to be able to focalize this to the tiniest possible spot. And this can be related to the mode of emission. It has to be a TEM00 mode. We need severe pointing stability, because if we have pointing instability, pointing is basically where the laser is shining. We can misalign the system mid-measurement. And also we need polarization stability, because we do some tricks with polarized light to be able to couple appropriately to our tip, and we need it to be stable. Well, in power of noise, in power and noise, we have less demanding requirements. We only require modest power on the south of 200 milliwatts. This is the absolute top that we would ever need. However, when we are using TERS, it's even less. It's less than 1 milliwatt. We need, however, a low relative intensity noise. We need it to be able to discern from where my system, my sample is and where it's not, and that's how we get low noise intensity. And it needs to be stable for a long time. Integration-wise, it needs to be compact. It needs to have a low thermal load, not to generate distortions in my whole equipment, and it has to have an extended lifetime to be able to ship to a client. And finally, operation-wise, we need it to be software controllable, we need a fast warm-up time, and we need fast modulation of wavelength. And now we can map how the single frequency Raman laser responds to these requirements. And spoilers alert, they respond great. The laser has 1 megahertz stability, 1 megahertz line width with stability greater than 100 megahertz, which is quite nice. It responds nicely to what we have on commercial available lasers. The spot is near diffraction limited with a single Gaussian mode. There's this one characteristic of lasers here, which is called the M square. It's basically how Gaussian this laser is. And for the single frequency Raman laser, it's less than 1.2, which is great. We can focalize very tightly. And it, of course, it's TEM00. Power and noise, we have data that gives us a figure of merit that's from 30 to 40% power conversion from the pump. Basically, this is the efficiency of the diamond that we are using. This is great. Then we can achieve the modest powers that we require for our techniques with this laser by using conventional pump lasers with less than 1% root mean square amplitude stability. Integration-wise, the neural models have a reduced footprint, which is great. We can directly integrate it in our TERS system. And operational-wise, we do not have an external cavity, which is very common in pumped lasers. This is great because it's extremely easy to align. I was able to align myself during my training in, I would say, less than 2 hours, which is a testimony about how good this technology is. And of course, we have the wavelength tunability and cascading that would allow us to have different wavelengths within a single laser. Well, this is just a comparison from the single frequency Raman laser with conventional alternatives. First of all, we have diode lasers. They fall short right on the first requirement because they are very spectrally impure, so it's a no-go. Then we have DPSS lasers, which are diode pumped solid state lasers. It's the kind of laser that we currently use. And in terms of spectral quality, beam quality, noise, and integration, they are good. Integration, not so much. However, when you think about operations, it's fixed wavelength. So we could benefit greatly if it wasn't. But unfortunately, due to the nature of this laser, it is. We have fiber lasers, which again have a poor spectral performance, which is definitely a no-go. And then we have dye lasers and titanium sapphire lasers, which are extremely fancy lasers, very nice. However, they're extremely expensive and very difficult to operate. So for equipment like ours, it's not a match. And then we have the single frequency Raman laser, which is a match throughout the whole board, which is great. And this is why we are selecting this technology to move on. This integration that we envision has 4 interfaces. First of all, is the optical interface. We have to be able to do proper beam delivery into our system. We have to condition the amplitude, we have to polarize, and we have to align it to the portal optical chain. Later on, we have mechanical integration, where we have to physically integrate it into our laser combining module or substitute it, which is what we hope for. And then we have electronic integration, which is triggering, synchronization, blah, 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 integration with electronic controllers. And finally, we have to integrate it into our software to be able to control it remotely. We have a very nice integration roadmap here. First of all, is a visit, the training and the tech transfer. That's where we are at right now. It's the first material accomplishment of this collaboration. And then after we receive the prototype, we will design an interface solution for this laser. And then we prototype and integrate the interface system. We validate it through a measurement campaign. And finally, hopefully, we're going to have the commercial release of a product that will be the portal with the single frequency Raman laser from CERN. And now let's move on to the horizons that we envision for the system. First of all, I'm going to begin with the simplest, which is the commercial pitch. Basically, what we have nowadays is when we're trying to use 4 different wavelengths on our system, I need narrow line width lasers, and they can cost about $10,000 each. So when we're stacking lasers, this can rise fast. However, multi-mode diodes are cheap lasers. They are very simple, and we can use the single frequency Raman laser as a mode purifier. So basically, instead of having 4 $10,000 lasers, we can have 4 $1,000 lasers, shine them into the single frequency Raman laser, and generate excellent laser lines, a multi-wavelength beam at a fraction of the cost. So this is a no-brainer approach to this. However, we can be more bold and think about CERN. So CERN is coherent anti-Stokes Raman scattering. It's a technology that has been used for a long time to characterize biological samples, especially label-free diagnostics. So what we have here is an image from this paper here that is the image of beta amyloid plaques from brain tissue. Of course, this is a mouse brain tissue, but the presence of beta amyloid plaques is being related to the early occurrence of Alzheimer's disease. So basically, before the person has the symptoms of Alzheimer's, they begin to deposit those plaques on its retina. So with CERN, we will be able to measure the patient's retina and look for these plaques and give an early diagnostic, and which would be amazing because we could start treatment early. Why is this not being applied? Because the lasers required for this technology are extremely expensive. Currently, the lasers used are dual OPOs, and they go on about 250,000 euros each. So this blocks out any possibility of having widespread equipments performing this kind of technology within hospital environments or even high-end clinical environments. But the single frequency Raman laser can substitute a dual OPO, and we would be able to create a system like this and put it on a hospital at a fraction of the cost. So what we envision is with this technology, we will be able to make cars get out of research labs and into hospitals, helping people's lives. And finally, we have fluorescence-free Raman. Basically, what we have in this technology is a technique called TERS, which is shifted difference Raman spectroscopy. What we do is we shine light into a sample at a specific wavelength here, collect a Raman spectrum. Here we have a Raman spectrum with very discrete peaks and a very big fluorescence background. So what we can do with this technology is we shift ever so slightly the wavelength, and then we gather another spectrum where the Raman peaks shift with the excitation wavelength. However, the photoluminescence does not. And then when we subtract these two spectra, we have this something that resembles a Raman spectrum, but it's interesting that it's naturally photoluminescence free. And with this in hand, we can use numerical methods to reconstruct the Raman spectrum, and then naturally we were able to minimize the background. This is extremely interesting because this here is an image that I put on for observation, but the Raman signal here is quite visible. Normally what we're dealing is our Raman signals, they're almost buried within the photoluminescence. So with this, we would be able to extend the reach and make it more easy to measure samples, for example, biological samples, pharmaceutical samples, geological and forensic samples. So this is something that might be native to the technology, which is naturally frequency can be shifted within the system. And we could directly use it to perform this kind of measurements. And with this, I thank you very much. Here are QR codes to every paper that I reference in this talk. And thank you very much for your time. I think it's best if I leave this here instead of a thank you, because if you want to gather any kind of information.
Many thanks, Vitor. Are there any questions? Wait.
Thank you.
So you showed mainly on graphene and
Yes.
let's say well-structured materials. What if we go to nanocrystalline or to even amorphous carbon? Have you done anything that you could extract information about extremely small domains? And
Yes, basically. Well, graphene is somehow our benchmark material, is what we use to assess the quality of newly produced equipments. It's a very interesting, very fascinating material, but it's not the only one that's out there. We also have active research in TMDs. So we measure a lot of MOSA2, MOS2, but also amorphous carbene. Yes, we have not published papers, but we have provided services for industry where they wanted to understand the distribution of metallic particles within amorphous graphene, sorry, I have all mixed up. So yes, we have been able to localize these features within graphene, amorphous graphene, and answering your question shortly.
And in terms of the structure, like say distribution of domains where you have sp2 hybridizations or sp3, is this technique giving some add-on relative to the standard Raman?
You could localize them in the nanoscale regime. Basically, what we can do is this. You can understand domain boundaries, which can be very interesting. And this can be used to map phase shifts within the structure. Yes.
Okay. Thank you very much.
Thank you.
Any other questions? Maybe some online?
Professor Granado.
Ah, sorry, yes.
I think you saw, very nice talk, by the way.
Thank you.
You saw in the slide 10, I think, pretty new results that you got with resonance of the plateau.
Yes.
And
they are.
But I don't know if it was a slide 10, but
Here.
actually before that one.
This one.
So is that plot in the top indicating that the resonance is stronger at a different wavelength, or which wavelength are you illuminating here always? Is it constant?
Okay, yes, it is constant because we have several different parameters. When we're talking about probe optimization, we have excitation wavelength, and we have physical dimensions, and also we have the alloy or the material to in which this system is built. This research here was conducted using 633 nanometers as a standard wavelength because that's what I did. That's how I did my experiments. Because this is not just talk, not just simulation. I validated with experiments, and this is quite interesting because going above a little bit about your question. These kind of tips and TERS, they are not supposed to work when we are using low numerical aperture coupling objective lenses. And with this technology here, when we play the plateau in the game, we are able to break that limit and use low numerical aperture objective lenses. So this, the motivation of this study is that I need to use long distance objective lenses for my PhD project. I'm trying to put this in ultra high vacuum. And well, according to the literature, it was a no-go. There are several papers showing that it's a no-go. However, our tip works like that. And we wanted to investigate why. And then we realized that the plateau interacts quite nicely with the radial component of light.
Yeah, very interesting. So I don't know if I got it wrong, but you're tuning the structure instead of tuning the laser, but you want a tunable laser.
Just
yes.
Kidding. No, yes, we want both.
Okay.
Yeah, because the production method, even though they're accurate, they're not perfect. So it would be extremely interesting if we can have a tunable tip and fine tune the laser to get the best signal.
Mm-hmm. Interesting. Thank you.
Thank you.
I'm just gonna read quickly. There is a question online. Thanks a lot for the questions. Why did you pick the 633 nanometers?
Oh, well, because it resonates quite nicely with gold, which is the standard material that we use here. This plasmonic resonance of gold is in the ballpark of 633 nanometers. So basically, that's why.
Thank you. Any other questions online or in the room? If not, then I want to thank you again for the nice presentation and for the very early stage application idea for the CERN technology of the Raman laser. We hopefully see soon some Alzheimer's application of that. That would be super cool to see that at some point. Thanks a lot for joining. Also, you guys, thanks a lot for joining for you. And if you have any other questions, of course, in person, feel free. He's still here for a bit. And thanks a lot.
Thank you.